DFS, we call DFS, we say as depth. Depth means hippie. Right? You want to find one node, and then you want to find next node, and then you want to go to the left, you want to go to the left node, you want to the left node until the end, and then we come back. You know, we can go to the left node, and then we come back. We can go back and then we go to the node. Now there is another way to do the search using breadth first search, or we call BFS. We will learn what is the concept of BFS, and we will learn what is the algorithm. And let's look on the problem. BFS means breadth first search. So before we learn the details about BFS, let's look more some graph property. In the graph, we can also get path graph. What is path graph? The path graph, or we call it linear graph, it is a path with at least two vertices is connected and has two terminal vertices. What does it mean? Terminal. What is the meaning by terminal? Do you know bus terminal? The idea with bus terminal. So if let's say we go from Incheon and then you go to your bus terminal, so it is the stop. But when we start from here, we can go to any node, we can go to any node, and then at the end we stop. So the path graph means there are at least two vertices is connected. It means we need to have the starting point and we have the ending point. And has two terminal vertices. So let's say this is the first terminal and then the second terminal. So this is the minimum requirement. Vertices that have the degree 1, so we call it the terminal. So we have the degree 1. It is also degree 1. While all others, if any, have degree 2. So in this case, this is where with the degree more than 1. So we can, because if we have only one for this node, then it will not be connected. So this node should be at least empty. This is the first, and the paths are often important in their role as subgraph of other graph. In which case they are called paths in that graph. So if I have this graph, there will be a path from this to here. So there will be a path from this to this, and there will be a path from this to this, and so on. So if we have a subgraph like this, then we got this is a path. That's another kind of graph. We call it bipartite graph. So the bipartite, or we call it pie graph, it is a graph whose vertices can be divided into two disjoint and independent sets. So we have U, we have V, such that every edge connects a vertex in U to one in V. So we can have one U. This is a protect, and it should have at least one connection to another protect in B. And this is the end. So if we have 1, 2, 3, 4, 5, and vertex in U, we have 1, 2, 3, 4 vertex in V. So there should be at least one connection between U and V. So we call this is the phi graph. Bipartite graphs are used extensively in online space. Usually, we use this for search advertising or e-commerce for the similarity ranking. For example, yeah, data for recommendation system. Then the U would be users. Who are the users? So this is the customer 1, customer 2, customer 3, customer 4, customer 5. And every customer is connected to an item. So this customer buys item. This customer buys this item. And when this customer buys this item, this customer gives a rating 5. When this customer buys this item, the customer gives rating 1. And so we got the bipartite graph. The bipartite graph is denoted as U and V and E. So U is a set of vertices, and V is another set of vertices, and E is a set of edges. U and V are the set of nodes, and E is the set of edges in the graph. In a graph, we can make the structure as a stack. Okay, what does it mean by graph structure stack? We call it the GSF. It is a directed acyclic graph. Do you know? Directed. Directed graph means we have a direction. Okay, so that's the meaning by directed. Acyclic. We call a graph with cycle. Okay. If there is a cycle, so if there is a cycle like this, then it is just common. But if we call it acyclic, it means it is no cycle. Okay. So directed acyclic means it is a graph with direction and no cycle. Okay. So acyclic means no cycle. Where its directed path represents a spring. So we can have this a direction, this is a direction, this is a direction. Okay, this is another. And this can be represented as one stack. So if you look at this detail, there will be 4 stacks. The first stack is 7, 3, 1, 0. The other stack is 7, 4, 1, 0. The other stack is 7, 5, 2, 0, and the other stack is 8, 6, 2, 0. Why do we need this one? The application could be in the natural language processing or maybe child. Okay, so in the natural language processing, we need to look at every of the text. So this text represent an adjective, and then this is also an adjective. This is a noun. The adjective with the singular noun, it represents a noun. Then this also represents a noun. This is a verb. This is an adverb. This represents a verb, and it creates that. So we can use this kind of graph to make another word or another sentence. So some of the GPT, they also use this kind of graph problem. We can also think the graph traversing with time. In the previous chapter, we learned the graph traversing using that versions. So the idea is the same with graph traversing using stack. So we can also use the graph traversing with stack. So until now, I think most of the team project, when you do the shortest path problem, okay, when you do the shortest path problem, most of you try to use the Dijkstra, and then you use the BFS, you use the DFS, you use the Bellman board. Okay, this is good. But if you want to have another challenge, you can try with stack. How can we use stack or problem? So let's assume that the starting point, yeah, is F. So we have this problem. So let's assume that the starting point is S. So we can visit the first neighbor of S. The first neighbor of S, we can kind of T. Then visit neighbors of the, let's say I T. Then I can visit the neighbor of T. Let's say the neighbor of T is P. Every time consider the neighbors of the last vertex visited. So we can say like this one. If I have S as the target, now next I will so T will go to the stack. And then I will visit V. Then I will put it in the stack. And then okay, I can consider W. If we use the DFS, we can consider W. If we use BF, we can consider the U and then W and the last. So at the end, we can find the parameter by pop this time, and then pop, and then pop, and then pop until the end of the step. We can also use Q to transfer the graph. If we use Q, mean whenever we visit a vertex, so let's say I start from F. Okay. I start from S, so visit the neighbor of F. Then I visit T. Then visit the neighbors of neighbors in turn. For example, I visit U, so I put, and then for example, I visit B, I visit W, and then I visit X. Then you can apply graph traversing with Q. As you know, Q is using the first in, first out concept. Then if I choose C at the first time, I will convert to visit C. And then I will visit U. And then visit V, W, X, and so on. So the algorithm of the breadth first. This is another algorithm as a general technique for traversing a graph. In BFS, the idea is similar with BF. We need to visit all the parts and we need to visit all the and we need to determine whether G is connected. Okay, G is a graph. And we want to compute the connected component. Compute the connected component. I have graph. Okay, I want to know whether this is a graph with connected component. If it is a graph without connection to a forest. So this is, we call it as forest because some of the graph is not connected. In this case, we call this graph with connected component. So we can use the breadth to compute the connected component. And we can also compute the spanning point. So we have the BFS on a graph with n vertices and m edges with O n plus m. So we can, and BFS can be further extended to solve other graph problems. For example, find and report a path with the minimum number of edges with 2 given per. Or we can find a simple sign if there is one. Okay, this is the algorithm for the BFS. The idea is the same with the BFS. At the first time, okay, the algorithm uses a mechanism for setting and getting label. So the input is a graph and the output will be the label, whether what is the edges and what are the vertices. At the first time, every U, it means for every vertex, it will be labeled unexplored. For every E, this is edges, it will be labeled unexplored. And if the vertices, so if all vertices, we go to all vertices, and if the vertices is unexplored, let's do, yeah. So the BFS will be this one. And the V will be, it will be the vertex. In the BFS algorithm, if you look at this code, you will see that there is a variable L. L0. L0 means the initial number. And if you go next, so we want to add S. S is the vertex to the L. L is a sequence. Then we can say L is a list. And then we will start with it and sub the I as Q. Now we will check Li. We have L2. We have Li. Li means a list of index I, and it will run until I plus 1, I plus 2, until the end. So if the LI is not empty, okay, then this is negative. No. If LI is not empty, then we will do this. We will start with empty sequence and then check whether all the V is in the element. If V is in the element, then we check whether they have the incident edges or not. So if we have the incident edges of V, then let's check what is the label. If the label is we have E. If this F is unexplored, let's check the opposite. And then check what is the label of W. If it is unexplored, let's set the E as discovery. And then let's set the W as visit. And then Li plus 1 will be added with W. And so on. But if uh, if W is already visited, then we set the label E as from. So if we have already visited a node, then this E will be set as cross edges. Okay, you can see the example. So this is the Python code. We can use the G as the graph, S is the node, and discover. So this is the discover node. So the starting point is the level. And then let's look when the level length is higher than 0. So it means if there are more than one level, then we will go to the next level. And then we will check for every of the level. And then check what are the incident edges of U. Let's check what is the opposite of V. And we put it up as the V. If V is not discovered, then let's put the E into the discover. And then next level, we will append the so the pseudo code is represent this one. This is the part. Okay, let's have a break.